And it's converting what to what?
Lactic acid.
To glucose. Okay, name another process that occurs in the liver. Enzyme? Converts what to what? Okay, give me another process that occurs in the liver.
The glucoamine cycle.
Enzyme?
Glucose 6
Converts what to what?
amino acid into glucose.
Okay, one more. Enzyme? Converts what to what? Good. So you need to know this terminology really well. There's a lot happening in the liver. 3 of these are happening during exercise and 1 is happening during rest. Which one is happening during rest?
Glucose or glycogen.
Glycogenesis is happening during rest. Okay, because during exercise, we're taking our substrates out of storage and mobilizing them so we can use them. So all 3 of these other ones are producing glucose to help us exercise. This one is putting it away for later. So this is the difference between a catabolic process and an anabolic process. You guys heard those words before? So catabolic is when you're breaking things down, and anabolic is when you're building things up. So if we're putting things in storage, we're working in an anabolic process. If we're taking things out of storage, it's catabolic. Okay, we're going to bring that up again next week when we do the hormones. So we're mostly focused on the ones that occur during exercise. We need to know how these all fit in and when they're happening. Questions on any of those? Yes?
Can you repeat the
Yes. Catabolic is breaking down. Anabolic is building up. Like if you think about anabolic steroids helping you build muscle, anabolic is building, catabolic is breaking down. Yes?
So Cori cycle, glucose alanine cycle, and glycogenolysis are all catabolic?
Yes. So Cori cycle and glucose alanine are probably technically not considered catabolic because they're not breaking something down, they're creating something out of something else. So if you think of that as catabolic, it's going to confuse you when we get to hormones. But they are happening during exercise and they are mobilizing substrates. Okay. In the ATP PCR system, we have this reaction. What's the enzyme for it?
ATP.
ATP synthase, because we're building the ATP. Okay, where does this energy come from in this system?
Electron transfer.
No, this one comes from the previous reaction.
Which reaction?
PCR breaking down.
PCR breakdown. In this system, the breakdown of PCR gives us the energy to build ATP. We have the same reaction in the electron transport chain, right? We do the redox reactions, we create energy to build ATP. It's the exact same reaction. The difference is where the energy is coming from. In this system, the energy is coming from the redox reactions in the electron transport chain. Okay? The purpose of all of our metabolic systems is to create ATP. The difference is where they're getting the energy from and how they're creating it. Okay? So this reaction we refer to as phosphorylation. Phosphorylation really just means you're adding a phosphate to something, so lots of reactions could be considered. Did I really write it like that? Phosphorylation. That's my brain getting way ahead of me. Phosphorylation.
Might need a break.
Phosphorylation means you're adding a phosphate to something, but in exercise physiology, we specifically use this term to refer to this reaction of building ATP. Okay, so this is also phosphorylation, but because the energy is derived from an oxidative process or an aerobic process, we call it oxidative phosphorylation. So phosphorylation is specifically referring to the anaerobic creation of ATP. Oxidative phosphorylation is specifically referring to the oxidative production of ATP, or the aerobic production. Yes?
On the study guide, you asked to describe the two, so would you go off of the definition you just described, or go more into depth about the differences in the?
No, you can just say, I mean, you can write this reaction and say phosphorylation is the anaerobic production of ATP. You know, you could be more specific, depending on how much detail I'm asking for. The energy for phosphorylation comes from the breakdown of PCR. The energy for oxidative phosphorylation comes from the redox reactions in the electron transport chain. It's oxidative. Because oxygen is being consumed in the process. All right, I know it's only been like a half hour since we learned it. Does anybody want to try explaining redox reactions? Go ahead.
So, the cytochrome will grab the electron that's coming from the hydrogen, and it will be reduced, and at the same time it will be oxidized, and the electron will be sent to the next cytochrome, which will then be reduced as well, and then it will continue to the next one, but that same one will be oxidized, and it will continue all the way until it gets out, and where it will bind to oxygen, and then hydrogen will make water there, and that energy will now be used into the oxidative phosphorylation
Very good. So where does that occur?
in the mitochondria.
In the mitochondria and the electron transport chain. So when I ask you to describe the process of the redox reactions, you need to use the words reduction and oxidation, and you need to tell me what they mean. So reduction means gaining an electron, oxidation means losing an electron, and during this process, what's being reduced and oxidized? The cytochromes. So the NAD is also being reduced and oxidized, but that's not considered the important part of the redox reactions because that part doesn't produce energy. It's the reduction and oxidation of the cytochromes that's producing energy. Okay, so that's really what we're talking about with reduction and oxidation. So use those terms, describe what they mean, mention the cytochromes. The purpose of this process is what?
To do oxidative phosphorylation.
To create energy for oxidative phosphorylation. You have a reaction with an enzyme to write for that. What is the enzyme for the redox reactions? Cytochrome oxidase. And what is the byproduct of the redox reactions? Water. Water is not the purpose. Water is the byproduct. What is the byproduct of anaerobic glycolysis? Yes. Good. Good.
So, as I just explained, the reduction and oxidation, do we have to mention the cytochrome oxidases? Or would that fit in?
You can just say the enzyme for these reactions is cytochrome oxidase. Okay. What are the 6 possible fates of lactic acid?
Heart,
Heart, liver, kidney, same muscle, other muscle, buffer.
kidney, buffer.
Liver. I think I heard them all. Everybody okay with that? Okay. What are the 2 possible fates of pyruvate?
lactic
Lactic
acid.
Okay, so what determines the primary fate of pyruvate?
Hydrogen density.
Exercise intensity.
Exercise intensity. How does exercise intensity determine the fate of pyruvate?
If you have
The amount of availability in the mitochondria and the electron transfer chain for hydrogen.
And what affects that?
the
The mo-
increase in
phosphofructose kinase.
The activation of PFK. Okay, so if you're trying to explain to me how exercise intensity affects the fate of pyruvate, at rest, what's happening to most of pyruvate?
going to acetyl-CoA.
Going to acetyl-CoA. As we increase our exercise intensity, we create certain conditions. Okay, so don't start explaining what happens if we activate PFK before you explain what's activating PFK. I know I tend to explain things backwards, but we need to reverse that now and go in order. So if you're resting, most of it's going to go this way. If you start increasing your exercise intensity, you're going to create certain conditions that are going to activate PFK. What are those conditions?
Decrease in ATP.
Increase in AMP. Increase in glucose 6-phosphate.
Okay? These can be in any order. These are not happening in order. These are all happening as a consequence of muscle contraction. Okay? What's causing the decrease in ATP?
Contracting our muscles. and
Muscle contraction, we have the reaction for that. What's causing the increase in AMP?
PCO reactions.
Muscle contraction, we have the reaction for that. What's causing the increase in G6P?
Liver, like,
What's happening in the liver?
The CoA cycle.
gluconeogenesis.
That is, but that's not.
Glycolysis.
So-
Glycogenolysis.
Here, let me explain why I'm not looking for gluconeogenesis here. In order to have gluconeogenesis, in order to have the Cori cycle, we need to be producing lactic acid to get the Cori cycle. My question is, what's causing us to produce lactic acid? It can't be lactic acid causing us to produce lactic acid. Does that make sense? So that's not what I'm looking for here.
Glycogenesis.
Glycogenolysis.
Glycogenolysis.
Breaking that down, our liver glycogen.
Glycogen into glucose. What's the enzyme for glycogenolysis?
Glycogen synthase.
Glycogen phosphorylase. Synthase is for synthesizing or building. Phosphorylase is for breaking down. Okay, so exercising activates glycogen phosphorylase. That's where you need to start this one. And I'm going to add another piece here. The next week we're doing hormones, so I'm going to introduce your first hormone here, which is epinephrine. As you increase your exercise intensity, your body secretes epinephrine. Epinephrine activates glycogen phosphorylase. Glycogen phosphorylase speeds up glycogenolysis, which means we're going to speed up our breakdown of liver glycogen, dump it into the blood as glucose, and it comes rushing into the muscle as G6P. This flood of substrate into the muscle we call an increased glycolytic flux. Like an influx of substrate into the muscle. Increased glycolytic flux. Now we have a lot of G6P. All three of these things activate PFK. What happens if we activate PFK?
We start speeding up the reaction more.
Speed up glycolysis, which causes
More hydrogen.
faster hydrogen production and therefore decreased mitochondrial availability, because it's full. So what's the consequence of that?
The hydrogen binds with the pyruvate, creating lactic acid.
And it goes this way. Okay, so the common error with this, remember the original question was, what determines the primary fate of pyruvate? The answer is exercise intensity. How does exercise intensity affect the fate of pyruvate? Well, at rest, most pyruvate is going to acetyl-CoA. As we increase our exercise intensity, we create these conditions, explain those, that activates PFK, and then explain the consequences of activating PFK. Common error here is to start at PFK. If you start at PFK, what happens is you say, okay, we increase our exercise intensity, we activate PFK, overwhelm the mitochondria, reduce pyruvate into lactic acid, and then lactic acid goes through the liver and creates glucose, which increases G6P. Do you see the problem there? So the question is, what's causing the increase in lactic acid? So the last part of your answer should be, and therefore increases lactic acid production. If you're following the lactic acid to glucose, you've missed the starting point. Because I'm asking you to explain the increase in lactic acid. The increase in lactic acid can't be the part of the explanation of the increase in lactic acid. So you've got to start with what's activating PFK and end with the increase in lactic acid. Did I lose you on that one? Jonathan?
I'm sorry, so where should we start? You said not to start at PFK, but where should we start?
You want to start with the things that activate PFK. So if I increase my exercise intensity, this happens, this happens, this happens. All three of these things activate PFK. Then if I activate PFK, it's going to cause this sequence of events, which is going to cause pyruvate to go to lactate. End of story. Cori cycle's not involved there. Yes?
You said there's no order for those three things, right?
Right, those things can be in any order. Yes?
For this part of the exam, will this be drawn or written?
Written. Go ahead.
So when we explain the third one, like an increase in G6P, would we start explaining that with epinephrine?
Yep.
And then follow it to that?
If you try to explain it backwards, it's going to get really messy. Yes?
Sorry, could you explain it like one more time?
The whole thing? Okay.
I'm sorry.
Okay. What are the two possible fates of pyruvate? Okay. What determines the primary fate? Exercise intensity. How does exercise intensity affect the fate of pyruvate? Well, at low intensity, where's it going? As we increase exercise intensity, we create the conditions of decreased ATP, we have a reaction that explains that. Increased AMP, we have a reaction that explains that. Increased G6P, the way we explain that is that exercise releases epinephrine. Epinephrine activates glycogen phosphorylase, which speeds up the process of glycogenolysis, breaking down stored liver glycogen into glucose. So we've got this flood of glucose coming into the muscle as G6P, which we call an increased glycolytic flux. That flood of G6P, along with these other conditions, activate PFK. If we activate PFK, it speeds up glycolysis, which speeds up the production of hydrogen. We're trying to bring hydrogen in the mitochondria, but it has a limited capacity. So when it fills up, mitochondria availability is low. There's not as much space in there available. Therefore, the NADH has to drop off its hydrogen and electron at pyruvate. Therefore, lactic acid production is going to increase. Okay. What is the enzyme that goes from glucose to G6P? What is the enzyme that goes from pyruvate to lactic acid?
Dehydrogenase.
What is the enzyme for glycolysis? Phosphofructokinase. What is the enzyme that converts pyruvate into acetyl-CoA? Okay, what are the three enzymes in the Krebs cycle?
Citrus,
Citrate synthase,
isos,
isocitrate dehydrogenase, and
succinate.
succinate dehydrogenase. Which of those is rate limiting?
The isos.
Good. Rate limiting enzyme for the electron transport chain. Very good. Any questions about any of that? We're ready for fat metabolism? Fat metabolism is not that bad. Not that bad. All right, when we're gonna do fat metabolism, we first have to take the fat out of storage. So triglyceride to free fatty acid, what's that process called?
Acidification. No, no, no.
Glycolysis. Enzyme, lipoprotein lipase. Okay, so lipoprotein lipase is going to be the rate limiting enzyme for beta oxidation, which is our fat metabolism, the beginning of our fat metabolism. Lipoprotein lipase is the rate limiting enzyme for beta oxidation. Okay, so once we've taken the fat out of storage, converted it into free fatty acid, then before we start the process of beta oxidation, we have to activate the free fatty acid, which is just a slight chemical change. You don't need to know anything about that, except that that process consumes ATP. So we're actually going to lose 2 ATP to activate the free fatty acid before we start beta oxidation. We're going to need to remember that when we're adding up the ATP. Okay, once they're activated, all of our free fatty acid will be in the form of long chains of carbon. They will either be 12 carbons long, 14 carbons long, or 16 carbons long. Those are the free fatty acids we have in the human body. They will all be organized into pairs. So we're going to start with a 12 carbon chain fatty acid organized into pairs. It's going to look like this. 2, 4, 6, 8, 10, 12. It's a 12 carbon chain fatty acid separated into pairs by high energy bonds. Now we're ready to start beta oxidation. So the process of beta oxidation will break one of these bonds and separate a pair of carbons from the chain. Okay, one pass through beta oxidation is going to break one bond. That reaction produces hydrogen and electrons that need to be cleared with the electron carriers into the electron transport chain. Okay, so we are going to get, from one pass through beta oxidation, we are going to get one NAD and one FAD, picking up hydrogens and electrons, going to the electron transport chain. How many ATP will we get from the NAD? How many ATP will we get from the FAD? For a total of how many ATP? 4 ATP each time we go through beta oxidation. How many times will this free fatty acid go through beta oxidation?
5.
How do you know that?
5 bonds.
This free fatty acid will continue going through beta oxidation until all the bonds are broken. So you count the bonds. 1, 2, 3, 4, 5. So this will go through 5 passes of beta oxidation. 4 ATP 5 times gives us 20 ATP. We okay so far? Okay. Remember that when I first introduced this to you, I said beta oxidation will always lead us into electron transport chain and the Krebs cycle. We never do beta oxidation without those. So, after a pair of carbons is separated from the chain, it's going to be converted into one molecule of acetyl-CoA. What does acetyl-CoA do for us?
Start the Krebs cycle.
Starts the Krebs cycle. One molecule of acetyl-CoA will give us one Krebs cycle. We have electron carriers here. What do we have up here?
Citrus, oh no, NAD.
3 NADs. How many ATP each?
2.5.
For a total of 7.5 ATP. What's happening down here?
1 ATP.
1 ATP. What's happening up here?
FADH,
1 FAD or FADH. How many ATP?
1.5.
For how many total ATP
10.
per Krebs cycle? 10 ATP per Krebs cycle. How many times will this free fatty acid give us a Krebs cycle?
6.
How do you know? What are you counting?
Pairs.
The pairs. Because each pair of carbons, once it's separated, will convert to acetyl-CoA and will initiate a Krebs cycle. So we count the pairs. 1, 2, 3, 4, 5, 6 times 6 Krebs cycles, 60 ATP. Okay, so I got 20 ATP from beta oxidation. I'm going to add that to the 60. I have 80 ATP. Am I done?
Nope.
I got to subtract the 2. Minus 2 for the activation. 78 ATP from a 12 carbon chain fatty acid. What was the maximum amount of ATP we could get from a carbohydrate molecule?
34.
33. So this is our shortest free fatty acid. So significantly more ATP from fat. Fat is a very rich source of energy, but it requires oxygen. It's slower. Questions on the process, the concept, counting? What happens during beta oxidation?
Electron transport chain and Krebs cycle.
Breaking a bond.
One bond is broken. One pass through beta oxidation will make one bond, will give us one NAD and one FAD, electron transport chain. Each carbon pair, after it's been separated, will go to acetyl-CoA, give us a Krebs cycle. So you have to know what's happening in the electron transport chain and the Krebs cycle to add up the ATP. Thomas?
There's no -2 under 88 from again?
From the activation before we started. We have to remember to count it at the end. Okay, here's what I want you to do right now. Account for the ATP from a 16 carbon chain fatty acid. Okay, don't just add it onto this. I want you to start from scratch, go through the whole process, calculate the ATP. 16 carbon chain fatty acid. Let me know when you get a number. What do you have? Let me know if you get the same number or a different number. Anybody else? everybody have it? Anybody get something different? Or if you're stuck, I'm gonna go through it right now. Okay, so -2 ATP to activate the free fatty acid. We go through beta oxidation that breaks one bond, gives us NAD, FAD, electron transport chain. 2.5 ATP for the NAD, 1.5 for the FAD for a total of 4 ATP. Times 1, 2, 3, 4, 5, 6, 7 passes through beta oxidation. 28 ATP. Everybody okay with that? Okay. Pair of carbons, acetyl-CoA, Krebs cycle, 3 NAD, 1 ATP, 1 FAD, all the details, total of 10. 10 ATP times 1, 2, 3, 4, 5, 6, 7, 8 Krebs cycles, 80 ATP, 28 plus 80 is 108, minus 2 for activation is 106 ATP. So when you're explaining this to me, you have to mention beta oxidation and explain what's happening. Okay, you can't account for the ATP from a free fatty acid without mentioning beta oxidation. Beta oxidation breaks a bond, separates a pair of carbons from the chain, gives us NAD and FAD. You have to mention the electron transport chain. You can't explain, you can't account for the ATP from a free fatty acid without mentioning the electron transport chain. You gotta tell me how many ATP from the NAD, how many ATP from the FAD, so I know you know where the 4 comes from. And then you can do the math. You gotta show me where you're getting the 4 from. Okay, you've gotta mention the acetyl-CoA, you've gotta show me the details of the Krebs cycle, so I know you know where the 10 is coming from. If you just put 10 there, you're not gonna get credit, you're not gonna get full credit, you gotta show me where you're getting the 10 from. Then you can do the math. Yes?
Will there ever be a time where like just the beta oxidation won't do the whole chain?
No. Beta oxidation will continue until the whole chain is broken up. And it will always feed into the electron transport chain in the Krebs cycle. So, cool thing about this, do you see where this connects to the other big drawing? This is the same electron transport chain that we use for carbohydrates. This is the same Krebs cycle that we use for carbohydrates. Krebs cycle doesn't know whether the acetyl-CoA is coming from a free fatty acid or from glycolysis. Doesn't make any difference. So it connects to that drawing. Not too bad. Questions on that one? Okay, it's either going to be 12 carbons, 14 carbons, or 16 carbons. You don't need to memorize the number, but you need to be able to figure out. Okay, one more concept in this chapter. This is the crossover concept. It's a graph. The x-axis is intensity. I'm going to say low, medium, high. The y-axis, I'm going to say percent substrate utilization. Low, medium, high. So this is basically how much we're relying on any substrate at any given time, carbohydrate and fat. So what percent are we relying on carbohydrate, what percent are we relying on fat as our intensity increases? So remember that when we're reading a graph, we're manipulating what's on the x-axis and seeing how it affects what's on the y-axis. That's why the y-axis is the dependent variable, because it depends on what we do to the x-axis. So in this case, we're manipulating the intensity, In this example, gradually increasing intensity, and we're looking at how that affects our substrate utilization. So we're gonna draw one line for fat and one line for carbohydrates. So let's start with fat. At low intensity, how would you describe our reliance on fat? It's high. Can it be 100%?
No.
Why not?
Because all these systems are always running.
Glycolysis is always running. We can't access our fat without glycolysis because it runs Krebs cycle. We can't survive without glycolysis, we would die. Glycolysis has to always be running, so we can never be relying on 100% fat, but we can be mostly fat. So it's high, I'm gonna put it right here. At high intensity, how would you describe our reliance on fat? It's low. Okay, so this graph says, as we increase our exercise intensity, our reliance on fat is decreasing. Let's do carbohydrates. At low intensity, how would you describe our reliance on carbohydrates?
Low.
It's low, but it can't be 0. So I'm gonna put it here. At high intensity, how would you describe your reliance on carbohydrates? It's high. That means as our exercise intensity increases, our reliance on carbohydrates increases. Notice there's a point right here where they cross over. This is why this is called the crossover concept. It's at this point where we shift from primary substrate of fat to a primary substrate of carbohydrates. Low to moderate intensity, our primary substrate is fat. Moderate to high intensity, our primary substrate is carbohydrate. At some point there's a shift. Notice also that that shift is at moderate intensity. Again, this was the point of your treadmill assignment. I had you starting at low intensity, gradually increasing until you felt a shift, started to feel a little bit uncomfortable, because when you're using fat at low intensity, you're primarily aerobic. At higher intensities is when you shift to start relying on your anaerobic system, and it's gonna feel different. So crossover concept says basically we shift from fat as a primary substrate to carbohydrate as a primary substrate as our exercise intensity increases. Do you have questions for me so far? Okay, this relates to this. If these are neurons, this neuron is connected to what kind of fibers? This one, this one. Okay, so if we're working at a low intensity, we're sending out weaker signals, we're activating our smaller neurons and our type 1 fibers. Type 1 fibers are good at what kind of metabolism? Aerobic. What is it about a type 1 fiber that makes it good at using oxygen?
Get to mitochondria.
Mitochondrial density, capillaries, oxidative enzymes, and myoglobin. So these fibers are really good at using oxygen. If we're using oxygen, we might as well use fat. If we keep increasing our intensity, we're going to need to activate our 2A fibers to help us produce more force and to create ATP faster. If we do that, these fibers, they can use oxygen, but they're not as good at it as the type 1s. So we're going to start relying on anaerobic metabolism. If we rely on anaerobic metabolism, we have to use carbohydrates. And then if we go even higher, we have to use even more carbohydrates. So the reason we're shifting to carbohydrates at the higher intensity is because we're shifting to our fast twitch fibers. Our fast twitch fibers are not as good at working aerobically because they have fewer mitochondria and all the things that go with it. So if we're forced to work anaerobically, we're forced to use carbohydrates. All these things are connected. What is this concept called? Principle of orderly recruitment or size principle. So you should be able to draw and explain crossover concept and relate it to the size principle. The reason we shift to carbohydrates at higher intensity is because we shift to fast twitch fibers. Fast twitch fibers are not as good at using oxygen. Forces us to use carbohydrates. Questions? Okay, how's your brain so far? Okay, so I'm pretty sure that's the end of chapter 2. So that leaves us with chapter 4 and then your exam. Chapter 4 is short, so I'm not going to start it tonight. What's going to happen